All right, Marcelo, we're going.
Yes, you're live.
We're on. Excellent. All right, welcome everybody to our final course in this year's SciNet summer school. Today and for the next couple of days, we're going to be discussing debugging, in particular debugging in high performance computing codes. For those of you that don't know me, my name is Eric Spence. I'm one of the analysts here at SciNet. My job, of course, is helping users making their codes go, and of course, lots of teaching, which we do to help people get things going. So, for those of you that haven't gotten it already, the material for today's class is at the first link here on this slide. You guys all have logged in already, of course, because you registered for the course. This is just a shortcut to that link. The slides are there, and the code for today's class is also there. If you want to download the code and follow along on your desktop or your laptop, that's fine. You can grab it there. Alternatively, I'll be doing some examples on SciNet's Teach cluster, and you can follow along on the Teach cluster as well if you prefer. As with all of our virtual summer schools this year, we have an attendance code to indicate that you were here. What's the code again, Marcelo? 7, was it? 7, there it is. Thank you. Attendance code is 7. So be sure to do your attendance code test so that we know that you were here. Here's a review of the details of the course. For you to get your credit for attending the class, you need to attend 2 out of the 3 sessions. The sessions, as you probably already know, will be today, tomorrow, and Thursday, 12:30 to 2, an hour and a half each. You'll have to do your attendance test, of course, and you need to submit the assignment, which we'll go over at the end of today's class. It should be pretty straightforward. It's heavily based on what we're doing today. It's all going to be serial stuff, so it won't be too complicated, I think. But we'll talk about that later. As with all things, I invite you to ask questions. We'll be monitoring the chat channel. Use the Zoom chat if you have a question, and we'll be sure to get you an answer as quickly as we can. I need to acknowledge, of course, the previous analysts who have developed this material I'll be presenting today. Much of it's been developed over many years. Bruno has been doing the development over the last few years, so I want to particularly give a shout out to him. I stole most of this material from him. So, all right, so today's class, we're going to be discussing debugging. The whole point of the next couple of days is debugging, guys. We want to get this into your head, to use good debugging techniques. Those of you that have suffered through a class, one of the longer classes that I teach and Marcelo and Alexi teach, you know we're all about using good coding best practices, and debugging falls into your toolbox of good coding best practices. So we're going to be dwelling on that a fair amount today. We'll be talking about GDB in particular, which is a very powerful debugger. And then finally, we'll round things out a little bit with Valgrind. I want to draw your attention to the fact that we will only be looking at compiled codes today and for the rest of this course, so Wednesday and Thursday as well. We're only going to be looking at compiled code, so C, C++, Fortran. We're not going to be looking at interpreted codes, so we won't be doing debugging in Python or R. By the nature of what we'll be dealing with right now. We're just going to stick to the high performance languages for this. As always, ask questions. Oh, we have a question already. Can the chat be recorded for reference after class? I'll let Marcelo answer that question. I think the chat is saved. We can post it probably. I'll leave that to him. He can fill us in there. Any other questions before we move on? Okay, excellent. So now those of you that have ever done any coding work, you know your workflow has looked like this at one time or another. I know mine certainly has. I'll be working on something, I'll compile it, it'll compile, which is great. You think life is good, and then you try to run it and you realize life is not good. Things have gone horribly wrong and your code seg faults. It dies a horrible death. And then you do some hacking of your code, you try this, you try that, and suddenly a great wondrous event occurs and suddenly my program works and it's fantastic and life is worth living again. Now, unfortunately, these steps between the red box and the blue box are not yet supported at SciNet. I haven't developed any supernatural powers that I'm aware of yet, so I won't be able to debug your code miraculously for you. The point of today's class is to get between the red box and the blue box in a systematic way. Something that is methodical, something that uses tools that are efficient, and approaches the problem of getting rid of your bugs and getting your code working in a systematic way, smoothly, methodically. That's what debugging is. That's what we're going to be trying to do today. We're going to be going over the techniques that we expect our users to use and what you ought to use when you're debugging high performance code, your C++ and your Fortran codes and those sorts of codes. Okay, now, generally speaking, there are two broad categories of mistakes or errors that you're going to run into when you're compiling your code and you're developing your code and you're trying to make it go, right? The first kind, of course, is the compile time error. And that means it's an error that develops at compile time. The compiler says, no, your code is bad, something's gone wrong, you're not doing it right, and I'm just going to shut down now. So the compiler in its own way is a great debugger, right? Because it'll automatically find bugs for you. All kinds of different bugs, like I've got a bunch here, syntax errors, library linking issues, you've got missing objects, you're linking to the wrong library or the wrong version of the library. All kinds of warnings can be thrown because of poor choice of casting variables or whatever. The compiler can do all kinds of things. It's really good at finding the very basic errors in the code. But these are syntactic errors, and generally speaking, they're easier to find. Linking errors, these are just sort of like technical problems, just getting the code to compile in the first place. We're not going to be focusing that much on compiling errors today, because obviously if you can't get your code to compile, you're not going anywhere, right? Debugging doesn't even need to happen at a more basic level because you can't get it to compile. So we're not going to focus on compile time errors today. We're going to be focusing on what are called runtime errors. Runtime errors, of course, are errors that creep up when you run the code. So you got through compilation was successful. Maybe we got some warnings and I probably ignored them instead of doing the right thing and fixing my warnings. You should always do that, guys. Fix your warnings so your code compiles without warnings. But then I run my code and bad things happen, right? Either I get a floating point exception or a seg fault, or maybe I abort, or I'm getting not a numbers all over the place, or who goodness knows what, right? Anything. There are all manner of different ways your code can die a horrible, horrible death that don't involve code that can't compile. These are called runtime errors, and those are the ones we want to focus on today because those are harder to find, harder to debug, because the compiler is an automated tool. It finds the easy things. You need another tool, something more advanced, something more subtle that can find your runtime errors. That's what today's class is going to be about, runtime errors, debugging. Okay, great. Now, as I've said before, as I mentioned already, if you've taken a class from SciNet before, we're very much about reinforcing good coding best practices when you write your code. As an analyst who's worked at SciNet for many years, I can attest that scientists, as a general rule, write really bad code. And this is because, generally speaking, they're not taught how to write good code. So you must, as a scientist, I strongly recommend you research and learn how to write good code. Here are some quick bullet points to show you how. First, you write clear, simple, straightforward code, sensible variable names, sensible function names. Goodness gracious, please comment your code. There's nothing more frustrating when a user comes to us and hands us a 10,000 line file of code that has no comments in it. Give us a hope, give us a hint. Most importantly, of all the bullets on here, I think the most important one is writing modular code. This can't be emphasized enough. Write code that is broken up into small chunks that stand alone, small chunks that you can pick up and move around and hand to your colleagues, small chunks of code that can be individually tested. Which brings us to the second last bullet, writing testing routines for your functions. So you've got your modular code, you've got code with functions that live by themselves, they're self-contained, you can invoke them when you want to. You write testing routines that beat the snot out of that function, make sure it does exactly what it's supposed to do. Write your testing routines, and of course, avoid cute tricks unless you absolutely know what you're doing, right? Sometimes doing things a little longer makes more sense than doing a shortcut to create code that ends up confusing you later on, of course. Now, this is, of course, just the very basics of coding best practices. You absolutely must use version control. Of course, I can't tell you how many times as a postdoc, I went into the office in the morning and by the end of the day wished I hadn't, because I was worse off at the end of the day than when I went in, because I was not using version control and I broke my code that day and I couldn't for the life of me figure out what the hose I had done to break my code. Use version control. That way you can back up, rewind your code to a place where it does work. It will compile. It does do what it's supposed to do. Be systematic, take note of your assumptions, and whenever possible, don't write code. This is something that a lot of new users often overlook, and that is use existing libraries, right? If someone's already written the code for you, goodness gracious, use it. It's out there by all means. You don't have to rewrite code that has already been written. Please use it. Okay, now, even the best coders who follow all of these guidelines, who write really modular, well-tested, solid, bulletproof code, still will get bugs. It's going to happen, right? You overlooked some corner case, you overlooked something that didn't seem consequential at the time. It's easy to sometimes overlook things. So even after all this, bugs will still creep in. Now, by using coding best practices, of course, we will keep the bugs to a minimum, but more importantly, it will make them easier to find. Okay. So, okay, you've got your code. You've compiled it. It crashes. You run it and it crashes. What do we do? What's the approach? How are we going to go about solving this problem? Identifying the bugs so that we can fix them. Okay, the first thing, as soon as you are convinced there is a real problem, which usually, if you're familiar with your code, shouldn't take too much work. The first step that you should always do is try to create a minimal reproducible example, right? The simplest example, the smallest amount of code that it takes to create the bug consistently. Whether either it's crashing the code or outputting incorrect values, whatever it happens to be. I used the word crash here in the first bullet, but it doesn't have to be a crash, right? It can just be incorrect values. Whatever it is, you want to be able to zoom in on the problem, right? Create the smallest example you possibly can, which reproduces the problem. Zoom in, cut away all the stuff on the sides that you don't need, make it as close to the problem as possible. After this, you want to, vary things a little bit, of course, right? Try a smaller problem size, turn off the compilation flags, make it a repeatable, and then we're going to start debugging. So we're going to zoom. The first thing you want to do, of course, is zoom in. If you can avoid using the whole code to reproduce the problem, and instead you can zoom in on it, so much the better. It'll be easier for you and it will be easier for the debugger to identify where the problems are coming from. So by all means, create the minimum reproducing example. Okay, now, so we're there. We've got our minimum example. The code generates the bug, crashes, or generates an incorrect value, whatever it happens to be. Okay, great. Now, what are the steps that we want to do? Okay, first thing you want to do, of course, is turn on all your warnings. The compiler's smart. They're very smart. They can see when you're doing bad things, even when you don't notice it. So turn them on. Okay, they're not, as it says here, they're not just there to annoy you, even though they do. They do give useful information. Turn them on, fix the causes of the warnings if you can, and you should. So most compilers are fairly forgiving, GCC and Intel. If you've ever worked with the IBM compiler, though, good Lord, good luck, man. They are sticklers. They will forgive you nothing. So it's always best to fix all of the warnings that the compiler gives you. It's also a good idea to stick assert, the assert function in your code. This, of course, if you're not familiar with assert, it's going to double check to make sure the left-hand side and the right-hand side of something equal each other when they should. So if this variable should have this value at this point in the code, double check. Those things can get stripped out by the compiler later. So you can stick assert functions wherever you want in your code, and that will help you to identify things sooner. Right? If you've got assumptions in your code, you can use assert to confirm that they're there. Right now, okay, so if your code is crashing, inspect the exit code. If you've got them, read the error messages if you get any. And then, of course, we step to the debugger. That's the next step. Do not use print statements. Please. Please, I know we want to, but don't. Okay? If you feel the need to start sticking print statements in your code to debug your code, go lie down, wait till the feeling passes, then get up and start using a debugger. Okay? Don't use print statements. Oh, we have a question here. You said -w all is used at compile time. It shouldn't have any effect on performance. No, it'll may slow down the compiling slightly, but it's not going to cause problems with your actual running code. What's wrong with print statements? There are several problems with print statements. First of all, it's slow, right? I have to add print statements. I got to compile again. I have to run again. And then I analyze the output. That didn't work. Go back, repeat, add more print statements, compile it again, run it again, blah, blah, blah. The biggest problem is that you're messing with the code all over the place, right? You're sticking in print statements all over the place. And that means you're going to have to go and unstick in print statements all over the place. And whenever you touch your code, it introduces an opportunity for new bugs to get introduced. And also, where is it? It's down here. Changes memory and timing. Problems with the approach. Time consuming, error prone, changes memory. This is an interesting thing. It has to do with memory bugs in your code. If you have memory bugs in your code and you start sticking print statements into your code, it can actually flush buffers at unexpected times and will actually make the bug show up in different places and make it even harder to identify. This is not something that a lot of people are aware of. I can attest to this from personal experience because I had, in my wisdom, introduced some memory bugs into my code and had started sticking print statements in, and they started showing up all over the place. It was really weird. Don't do it. Print statements can cause other problems if you have memory errors in your code. Don't do it. Okay, there's a better way, and that involves debuggers, which is why you're here today. Okay, debuggers. Now, before I even start, I'm just going to say what I say to many students, and that is that, yes, there's a learning curve here. Yes, the debugger takes time to master, and it takes time to get yourself in the sort of zone where you want to use it or you instinctively reach for it. It's kind of, in that sense, it's kind of like version control, right? It requires a change in your lifestyle, so to speak, your coding lifestyle, if you will. And when that happens, there's always resistance. I never like, I'm an old guy, I'm set in my ways, I don't like to change the way I do things. But I promise you, as with version control, if you learn to use a debugger, familiarize yourself with how it works and the basic commands and how you launch this thing and how you get going, it will become a powerful tool in your toolbox. As a coder, as a developer, as a scientist, this is an excellent thing to learn how to do, despite the pain that there may be at the beginning. And even there isn't that much pain, to be totally honest with you. It's not like it's ridiculously foreign. It just takes a little bit of getting used to. Okay. Debuggers, also called symbolic debuggers, are programs which have been specifically designed to find bugs. They're used for code crash inspection, finding the function call stack, stepping through the code, variable checking, variable setting, all manner of poking and prodding of the code in a live setting. So you don't have to keep print statement, print statement, print statement, trying to figure out what you're doing. Okay. These are specific tools designed specifically for this task. So you should intuitively start thinking, okay, well, that makes sense. This is the tool I ought to be using. It was designed for this. And assuming the designers know what they're doing, then it should be the right tool for the job. And that is true. It is the right tool for the job. Learn how to use it. That's why we're here. Okay, so some debuggers have a graphical user interface. Do I want to use it? Maybe, maybe not. Okay, graphical is convenient on your workstation because the response time is very fast. If you're running X windows of any kind over the internet, unless you've got a really good internet connection, it's going to be slow and kind of clunky. So you may not want to do that. Alternatively, many debuggers that have graphical user interfaces have what's called a client server mode, which means that the bulk of the work can be done on the big machine and you just have a visualization end running on your local station or your laptop or whatever it is. And this allows the amount of communication to be much less. And in that case, it works out fairly well. In any case, they all sort of have the same principles. And so once you become familiar with the techniques you use in one debugger, you'll be in pretty good shape to use just about any of them. Now, today we're going to be using GDB, the GNU debugger, which is a text-based one, not a graphical one. So it's pretty lightweight, and you can use it over an internet connection with a terminal if you want to. We'll get to that in a minute. Any questions so far? I'm new to coding this summer. How do you differentiate between having a problem in the code and writing code that does something different from what I wanted? I don't. They're both bugs. The exact nature of the bug depends on what it is and what it's doing. I think I would need a more specific example to come to that, to answer more specifically. Bugs are bugs. Debuggers can be used in either case, whether your code is crashing or whether it's just doing the wrong thing and you don't understand why. All right, so how do we go about using a debugger? Sorry, I know that's not a very satisfactory answer, but I'm afraid without a specific example, we can go over it more later if you like, maybe tomorrow, or you can email us or text us directly, whatever. Okay, so how do I go about using a debugger? So there are two steps to using a debugger. The first step is with your compiled code, you need to compile with the compiler flags which add the symbols to the executable. So by default, there are no symbols that tell the debugger where we are in the code and what the code is doing and whatever. Those things are not added. The general flag, the sort of semi-universal flag that is used for adding symbols, debugging symbols to your code is -g. All the compilers use it as far as I know. I'm not sure if all of them do, but as far as I know, all of them do. dash lowercase g. I also recommend when you're debugging to always turn off optimization. So use -0. Now you can see down here in this code block the different flags that are available. So if you're using GCC or G++, you use, like I said, dash lowercase g. You can also add the -g stabs flag. You can, I suggest looking at the man page for GCC if you want the details about what those do. I usually just use dash lowercase g. That usually is sufficient for my purposes. Same with the Intel compiler, dash lowercase g. There's also a debug parallel. And finally, with CUDA, there's lowercase g and uppercase g. Again, the specific details about what each flag does, you'll have to look at the documentation. The dash lowercase g is usually sufficient to get you going. But depending on your specific needs, you may need to add one of the other flags as well. Okay, so we've added our extra compilation flag to our compilation line in our make file, for example, or when we compile things at the command line, we add a -g. Great. Now what do? Well, now you just launch the debugger. It's that simple. So you launch the debugger using the code. Okay, so how do we do that? Well, we'll do that in a second. Let's talk about GDB first. Okay, before we use a specific case, let's talk about GDB. Okay, so GDB is the first debugger we're going to use today. It's been around a long time. It's called the GNU debugger. That's where GDB comes from. It's free, open source, GNU debugger. It's been around like 20 years or something. It's a mature product, but it's constantly being developed. So it's up to date. It's available on most Unix-like systems. Scynet's Teach cluster and MIST, if you're using the GPU cluster at Scynet, have GDB available as modules. Niagara itself has GDB built right into the operating system image, so you don't have to load a module. It comes right with. So that's one less step if you're using Niagara. Works on many languages, C, C++, Fortran. If you're using Ada or Go, it sort of works. You'll need to double check specifically what you're doing. I think it works on Ada. Go, it has some issues with, and that's just the way it is. There's only so much that it can do. Does GDB support Julia? I do not know. Does anyone know if GDB supports Julia? I don't think so, but that's a just-in-time compiled language, so it may be different. It does. Oh, geez. Thank goodness I have a backup team here. This is awesome. All right. Go team. All right. Text-based means it's easy to use in a terminal. It means it's lightweight over an internet connection, so that's good. But it also has a -2e option, which stands for text user interface, which allows a few fancier features for your code in the terminal. We're not going to be looking at it today, but if you become familiar with GDB, I recommend playing around with 2e if that's your thing. It's not my personal taste, so I'm not going to be showing it to you today, but some people like it. So excellent tool for debugging. Okay, as I said, we'll run some examples on the Teach cluster today. You can also install it on your own local machine and use it there. In fact, that's really the way I would recommend doing it. If you're watching this lecture from the machine that you usually work from, I would recommend downloading and installing GDB. If you do any sort of compiled work using a code that's compiled, you may as well get it installed right now and start playing with it, right? Because it's easy to install as a general rule. It's pretty straightforward. And it's a tool you ought to be using. So if you're going to be doing your development on your desktop or your laptop, I recommend downloading it. So the link is there for downloading it. That just sends you to the source code. That's not necessarily the most useful thing. If you're on a Mac, I recommend using Brew or Fink, whatever your favorite package manager is for your command line packages. I personally use Brew on my Mac, and it installed in like 10 seconds. It's not very big. and it just zipped right on. If you're using the Windows subsystem for Linux, the Linux Ubuntu distribution that you can use with Windows 10, you can just use apt-get install GDB. It's a package that's in the standard repositories. It's one line and off you go. Otherwise, I'm not sure how you would install GDB in Windows because I know nothing about compiling code in Windows. So you're on your own. Good luck. Let us know how it goes so that I can fix this slide for next time. On Linux, of course, you just install it the usual way with your favorite package manager. So apt-get or yum or whatever. Or if you prefer to install it from source, that's always an option too. Okay. If you're installing stuff, I recommend you also grab Valgrind as well while we're at it. So if you're using Brew or using apt-get or yum or whatever package manager you're using to install your packages, I also recommend installing Valgrind as well right now, just because we'll be using that later in the class and you'll also need it for the assignment. So that's recommended as well. Questions? Get a sip of coffee here. GDB GUI. Oh, Bruno's right. I forgot about that. GDB also has a GUI called DDD, which I haven't used in a long time. I don't know what its status is anymore. Okay, very good. So, getting set up on SciNet. So if you're interested in running on the Teach cluster and doing a few examples, these are the steps we're going to do. I'm going to follow along here so we can see it together. So we're going to SSH into the Teach cluster. Now, obviously, you've got your own login name. Don't use EJ Spence because that's me. All right, SSH in, type password. Okay, now we're on the Teach cluster. I'm going to CD into my Scratch directory so that we're not working on home. And then the code for this class is in this directory that you see on the slide, /scinet/course SS2020 11debug. Now, those of you that downloaded the code from the class website in the tarball, same code. It's the exact same code. So if you're working from home, just download the tarball from the website. It's pretty small because it's just code. There's nothing fancy, no data or anything in there. It's just code and make files. So it's pretty lightweight. So you can follow along using the code in the tarball there. I'm going to copy this whole directory over to my Scratch directory so that I can mess around with it there and not mess with everybody else's stuff. So 11debug, and then I'm going to copy it into my Scratch directory. And then I'm going to CD into that directory. So now I'm in the PWD Scratch. This is where I am. Scratch S SciNet EJ Spence. That's my Scratch directory. Obviously, you will have your Scratch directory. It will have a different path. So don't get confused. If you're new to SciNet, you'll have a different path there. You won't use the same path that I will, and that's correct. Okay. Let us know if you have any questions about getting set up. We've got lots of helpers online today. So throw a question into the chat or ask for a breakout room and we can help you, but it's pretty straightforward if you've ever used the command line before. Alternatively, of course, if you don't want to do the examples right now, you can always do it on your own time. Send us an email if you have a problem or are there any questions. I'm going to just change this aspect ratio a little bit here. Okay, good. Okay, so now we're going to march through a GDB example for much of the rest of this class. We're going to march through the example and I'm going to introduce you to the techniques that you can use to identify where your code is going wrong. Many of the commands that are available, within GDB that do various things. We're going to march through them all so you can familiarize yourself with some of them. And yeah, that's what we're going to, sorry, I'm going to lost my train of thought there. Okay, so if you LS, you'll see there's a file there called setup. I'm just going to source the setup file. Okay. All that's doing is loading the modules that we're going to need today. It's there's not much to it. You can look at it. All it's doing is loading the compiler, OpenMPI, GDB, Valgrind, DDT, all the stuff that we need for today and tomorrow's classes. That's all the setup script is doing. Now for the rest of this class, I want to do an example called bug example. So I'm going to move into that directory. So now I'm in 11 debug bug example. And then I'm going to do make. Now, this is going to, so maybe we should just ls first so you can see what's in here. So there's not much in here. We've got some header files, we've got a few pieces of C code, and we've got a make file. What this make is going to do is it's going to compile this particular piece of C code. There's not much to it. It's very small. It compiles almost instantaneously. Okay. This code is very simple. All of this code is going to do is take some integers from the command line, read them in, sum them up, print out the answer. That's all that the code does. Very simple, not much to it. And yet, as you'll see, it's got lots of problems with it, which is why we're going to be debugging this code today. Okay, questions so far? Oh, here's another thing I forgot to mention. Please, please do not use copy and paste out of a PDF. If you've got the slides in front of you and you're trying to copy things, please don't try to copy from the PDF. If you try to copy and then paste into a terminal or into a text editor, you may get things that you don't want. Okay, there are hidden characters living in the PDF that you can't see. If you do copy and then paste, they'll paste them into the terminal. You still won't see them. Things won't work. Type everything out you see by hand, please. Okay, so let's start our example. So I ran make. So I now have my executable. You can see it over here, bug example. Okay. Now what we're going to do is we're going to try to run this guy. So what's going to happen? Okay, so first I do bug example. Dun, 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 dun. It says, no, you fool. I want some integers because that's what this code does. It adds up integers. So I'm going to give it, I don't know, 2, 5, and 6. Fantastic. And kablooey, yes, as you would expect. This is a debugging class, so I get a segmentation fault. Okay. That's not very helpful. Now, for those of you that are new to compiled codes, you should know that segmentation fault represents, generally speaking, something to do with memory. Either you're accessing memory that is out of bounds, that you haven't allocated, you're trying to deallocate a pointer that doesn't have anything allocated. There are all kinds of different things that a segmentation can refer to. Generally speaking, it has to do with memory access, illegal accesses of memory, that sort of thing. Now, unfortunately, this error message that we've got here is not very enlightening. Segmentation fault tells me that it's probably a memory thing, but that's not sufficient to actually get me anywhere. So what I'm going to do next is I'm going to do this command here, ulimit -c. Before I type it, let me just explain what it does. So ulimit -c is used to indicate or change the maximum size of the core file that will get dumped by the code. So if I just type ulimit.c, you'll see that I get a 0. And what that means is I am not going to dump a core file. The code will not dump a core file if seg faults or something else goes wrong. It's just going to stop. And that's what we saw here. Now that's not very useful. I want my core file. So I'm going to change my ulimit -c to 1024. Enter. And what that says is it's going to change the maximum size of core file that can be dumped by the code. Now if I do bug example, /bug example, 3, 6, 7, whatever, enter. Now I still get my segmentation fault, but now I've gotten a core dumped. And that's what you see in the brackets there, core dumped. Now, why is this important or why is this helpful? A core file contains the state of the program, the memory state of the program at the moment that the code failed, at the moment that the code crashed. It contains the in-memory state of the program. It's also called a core dump. You dumped your core. How embarrassing. So this is useful. Now, if you ls, you can see I've got my core file here, core 9876. Yours is going to be different. It has to do with the process ID of the code that crashed. So you're going to have a different number. If you're working at home, if you're on a Mac, for example, you may not get the .pid core file. You might just get a file that says core, and that's it. On my laptop, when I was testing this code earlier, I found that there was no dot extension. It was just core, and that was it. So don't be surprised if you don't. It can be named different things. The important thing here is that we've captured the memory state of the program at the moment that the code crashed. Now, the reason this is useful, as you might imagine, is that the debugger can use this. The debugger can use this to help diagnose what's gone wrong with the code. Operation not permitted. Where are you when you do ulimit Isaac? Ulimit -C 1024. You're not allowed to change the ulimit? Where are you? On your own machine or on the teach cluster? Interesting. I'll leave that for Ramses to respond to. Ramses, do you know anything about that? All right, we're going to move on while we think about that. I didn't realize that I was the only one that was able to change the ulimit -C. I wouldn't have thought so, but I am more powerful than your average user. Okay, so while we're thinking about that, GDB will inspect the core file to try to figure out what's gone wrong. So what we're going to, there are a couple of ways that you can now launch the debugger. So as we said before, the first step was compiling your code with the -G flag. This adds the debugging symbols to the code. Next, you want to run it with the debugger. Now, you've got two options here. The first option you can see here in this first bullet, and that is to give the core file to GDB. So you can do GDB, name of the executable, and then the name of the core file. And that will help GDB figure out where you are and what went wrong. Alternatively, if you don't have a core file, you can just launch it without. You can just say GDB and then the name of my executable, boom. And then you type run and then run with the command line arguments that you want to pass to the code, and GDB will start running the code, and eventually it will crash and you'll run into the same, presumably the same location that you did when you ran it from the command line. So we've already seen a couple of commands in GDB. Run, we're going to run into list in a minute. List, we'll list the code around the spot where you've crashed. So let's just go straight to the example so you can see what I'm talking about here. So I've got my core file, there it is. So I'm going to do GDB, that's the name of the debugger, of course. I'm going to do bug example, and then I'm going to do core, enter. Okay, so what do we see here? Let's go through this. So at the very beginning, all of this stuff here, that's all the introductory, welcome to GDB, blah, blah, blah stuff. Great, okay. Now it's going to start talking about what it's actually looking at, and that's right here. So reading symbols from bug example, great. A core was generated using this command, okay. Program terminated with a seg fault, segmentation fault, we knew that. Now, here's where things start to get useful and interesting. The code crashed in this function, some integers, with taking these arguments in this file at this line. And this was the line in question. So you can see already we've gained a lot of information that we didn't have before, right? We've identified one, that the segmentation fault crashed, or the code crashed with a segmentation fault. We knew that already, fine. We identified where it was in the code. We've identified which function it was in, what the function was called with, and not only that, the specific line of code where things crashed, where things went wrong. We're already way ahead of our print statements, right? We did this all in one shot. Boom, the code crashed. Here's where it crashed, in what function, in what file. Boom. Good. Okay, now here's an aside I want to draw your attention to. If you are unfamiliar with debuggers, if you've never used a debugger before, if you use compiled codes in any way, I want you to notice the advantages already that you can see, right? What GDB is, let me just show you. I'm going to hit enter here. We've got a GDB prompt now. We've got an interactive prompt in GDB. GDB is living, so to speak, living inside the code. It's not quite right, but you can sort of think of it that way. We, by sitting at this interactive prompt, are now living inside the code, a live code, a code that's actually running with variables that have actual values and functions that have actually been called. Now, yes, okay, the code's not running right now. It's actually been paused, but the code is still live, right? We can start doing things because we're inside an actual code that's actually using, that's actually running, excuse me. We can poke around. We can start asking questions like, what's the value of that variable? What assumptions have we made? Can we check them while we're in here? Because we're actually in there. We don't have to stick print statements in that check this and then check that and check this and check this and recompile and run and recompile and run and check that. No, 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 none of that nonsense. We're in the code. We're right there. We can wander around inside the code, poke things as we want, figure out where things are going wrong. You can see the advantages already. Okay. No print statements, no recompiling needed. Using a debugger is the correct tool for this job. Okay. All right, sorry, I'm getting distracted by the chat. Don't forget to source the setup file. That's where you load all the compilers there, James. All right, so here we are. So we're in GDB. We've run the code with the command line arguments and the core file. GDB knows where we are. We're on line 30. Remember, that's what we said here. We stopped at line 30 because that's where we crashed. Okay, now I'm going to use the list command. Now, list is going to print out the code surrounding the line where we just crashed. In particular, it's going to focus on the lines before where we crashed. So you can see here on the left-hand side are all the line numbers of the code. It doesn't print them all out, obviously. It's not going to give you the whole file. This is small code, right? You could have a code that's hundreds or thousands of lines long. You don't want to print them all out, obviously. We're just going to print out a little bit. That's what list does. And you can see here, you'll forgive me, the indentations didn't show up on my slides, but you can see them here on the right-hand side. We're inside this function called sum integers. It takes 2 arguments, and it looks like it's adding stuff up. Okay, great. So GDB's list command can be used to print out the code. The line numbers are on the left. Now, one thing about GDB you need to be aware of, this threw me for a loop the first few times I was using it, is that if you hit enter at the prompt, it doesn't just do nothing. That's what intuitively I was expecting, right? When I'm at my standard Linux command line, if I hit enter and there's no command, nothing happens. That's not what happens with GDB. With GDB, if you hit enter and there's no command, it will try to rerun the last command. It doesn't do nothing. It reruns the last command. Now, it turns out that if you run list multiple times, it doesn't redo the list. It actually tries to keep printing from where you are. The next block of code. Now, this particular file only has 32 lines of code. And so if I hit enter again, GDB is going to try to run list a second time. It's going to try to print out the code starting at line 33, but it says, no, there is no such thing. That's where this error message is coming from. So no need to freak out. That's where that's coming from. But be aware, if you hit enter and there's no command, GDB will try to rerun the last command. Now that depends on what the command was. List, it will try to rerun, but certain other commands it won't. There's a slight inconsistency in the behavior. It depends on if it makes sense to rerun that command. All right, questions? Okay, I'll leave you guys to take care of these guys over there. Okay, so now, so what is my approach when I'm trying to tackle a debugging problem? How do I go about doing it when I'm inside GDB and I see that there's been some sort of problem? One of the first things that I like to do is get the function call stack. Now, there are a number of ways to get it. One way is to just run the code in GDB using the run command from the beginning rather than using a core file. And then hitting Control-C, which interrupts the code, and then it will stop wherever it was. However, I like to get the stack trace, which a stack trace, if you're not familiar with the idea, is the list of function calls that led to where you are right now. So generally, the very first one will be main, and that will be followed by main or whatever the main function is that runs the whole program, the main program. Main followed by some other function, followed by some other function, potentially followed through many, many, many functions that are calling one another. It's good to see where I am in the code. How did I get to where I am right now? That's what the stack trace will tell you. Now, how do I get the stack trace? Well, I'm going to use the, how do I do it? Where is it? Backtrace function. Oh, it's just right here. The backtrace function. Print out the function call stack. There are many other commands. We're going to go through a whole bunch of little tables like this over the course of this class. Here are a few more. Frame, which is a good one. It prints out where you are in the code right now. Up and down are also ones that I often use when I'm debugging. And up and down, what they do is they go into the calling function or they back out of the calling function, depending on what you're doing. So if I'm inside a function, I can use up and that will pop me out of the function back to up one level, for example. Okay, so let's go back here. So where am I? So I'm going to type frame again just to remember where I am. So I'm going to type frame. It's going to say, oh, yes, I'm at line 30 in the file int list tools. And this is what the line 30 is. S plus equals a at I. And that's inside the sum integers function. Great. Now I'm going to type out backtrace. So like I said, this is going to print out the functions that were called to get to where we are right now. So as you can see at the bottom, sorry, I said the first function, it's usually the last because it goes in reverse order because it's a stack. At the bottom is main, that's the main function. And then that called process, or at main at line 12 called process, and then process line 11 called sum integers, which is at line 30 in int list tools. So this tells you, okay, how far in the main program did I get before I crashed? Okay, I got to this line, great. And it called this function. And I got this far down that function before it ran into problems calling this function over here. And then I made it to line 30 inside this file when things started to go south. Useful information. This is what I used to do. This is all the information I used to get when I started putting print statements in my code, right? That was essentially what I wanted to find out. 9 times out of 10 was just the stack trace. How did I get to where did it crash? That's the first question. But not only where did it crash, how did I get there? How far in the code did I make it before it crashed? So I can start testing the assumptions, checking the values of variables to find out why this thing went south, right? That's what the stack trace does for you. Again, no print statements needed. Beautiful, beautiful. Okay, so now, once I've got my stack trace, I know the line number that I failed at, I know in what function things went wrong, I can start checking the values of variables. I can start poking at things, trying to figure out where did things go wrong? What should this variable's value be? You know, do things look suspicious? Do things look fishy? Or do things look okay? This is how I can start checking, right? I can start using print statements. So we've got a few functions here that are pretty powerful. I use the print statement often. So I'll say print whatever, print some variable, and then it will print out the value. This is the value of the variable right now. At the point that the code crashed, this is what the value of the variable is. Cool, great, all right. Now I also use display quite a bit, display variable. Now display is the same thing as print, but the difference is that it is going to keep printing the value of the variable after every time something is done. So you type in the next command, and then it prints out the variable again. Type in another command, it prints out the variable again. It just keeps printing it over and over and over again. And the reason for this, of course, is that I'm going to start poking around. I want to move through the code. I don't want to have to keep writing out print this, print this, print this. No, no, no. It'll just give it to me. Print, here it is, here it is, here it is. And you can watch the value of that variable change as you march down through the code. Cool. All right, that's way easier. Excellent. Another thing that is sometimes fun to play with, though can be a little dangerous, is set. And that is, I'm just going to march right into the code and start messing with the values of variables. I'm going to change a value using the set command. Set this equals that. So I'm changing it explicitly. And then I say run or continue, and it will carry on with the code, and you can see what happens. It's sort of a what if situation, right? Okay, cool. So I'm in my code here. Notice when I hit enter without hitting any commands, it just keeps running the backtrace function there. Backtrace can be called as many times as you want. So I'm going to list again. So there's list. Okay, so remember, we're on line 30. You can also list it with line numbers if you want. 25, 32 does the same thing. And it's going to list from line 25 down to line 32, inclusive. Okay, great. So you can see here that we've got a variable s, and we're assigning it a value a at I. So I is an index. Let's check the value of I. I has a value of 0. Okay, that's fine. Clearly, this is the first time we entered the loop, right? I is equal to 0. If you're familiar with C or C++ for loops, I equals 0 is the initialization. And so clearly, when this crashed, it was the first time through the loop because I still has its original value. Okay, great. So I is not the problem. It's doing what it's supposed to. What about A at 0? We know that the problem is in here somewhere. Let's check that. Okay, now we can start to see a problem. Cannot access memory at the address 0x4. Now, whenever you see a 0x, when you're poking around in GDB, that indicates that you're dealing with a hexadecimal number. So don't worry about that. This is the normal way that memory addresses are indicated when you're using GDB, using 0x. So that's normal. But this looks suspicious because this is a very small number. Let's just print A itself. It says, okay, this is a pointer to a variable. Actually, this is probably a null pointer. Someone who knows more about this can correct me. I'm pretty sure that's not a null pointer because that's not a 0. Nonetheless, it doesn't look like a properly initialized array. We're going to come back to this in a minute. Okay. So we've got a hint here that something's gone wrong with A over here. This line, it's not I seems fine. It seems to be A. A seems to be an uninitialized vector that we're trying to add up elements from, but we can't. That doesn't, you can't add up the elements of a non-existent vector. And that's what seems to be the problem. Let's keep pushing forward and see what we can come up with. Now, I told you before about the function or the command up in GDB. Remember what up does. Up is going to pop us up out of the current function. So currently, we're sitting at line 30 in the sum integers function, this guy here, right? Now, something's wrong with A. We've determined that. We've got an empty vector here. Now, A is an argument to this function. Sum integers takes this vector A as an argument, a pointer to an array or a vector. So let's pop out of this function up. We're going to pop out of the function to where sum integers is called so that we can look at the argument. Because remember, it's this argument A that's the problem. A is not being messed with inside the code of some integers. So the problem must be outside this function. So I pop up and I can see, okay, so some integers. So now look at where we are now, right? So I'm going to do frame again, frame. You can see where we are. So we are no longer in int, what was it called? intlist_tools.c. We're not in intlist_tools.c. Now we're in process.c, line 11. Int s is assigned the value of some integers n and arg. Now, if you look at the arguments of some integers, the first argument is just an integer. The second argument is the pointer to a vector. That's this one here, right? The one that's causing problems. A's got problems. Now A over here is arg, right? Arg is getting passed into the function. Let's check arg then. So I'm going to do print arg. And there we see the arg variable is again an empty pointer. Same problem that we saw with A. That makes sense, okay? That's no surprise, really. That means that intuitively things are going correctly in the sense that the value of arg got passed into the variable A and then got passed down into some integers, and that's where things went wrong. But the problem was not in some integers itself, because the variable that it got, the pointer that it got, was never initialized in the first place. So that this is a better hint as to what's gone wrong. The problem isn't in some integers, it happened before that. I'm going to hit list again. So now I print list, we can see where we are now inside process.c. We're inside this function called process. It takes 2 arguments. And remember, we're on line 11, this line right here, where some integers was called with the argument arg. And arg comes from this guy over here. It comes from read integer arguments. That's where arg is coming from. Okay, good. So this gives us a hint of where things are, where the problem may have been coming from. And that is that the variable arg took the output of the read integer arguments function. Maybe something went wrong there. Gives us our next hint of where to look for problems in the code. Okay. Now, another tool that you can use when you are debugging, and this is another one that I use often when I am doing debugging of codes, is what's called a breakpoint. Automatic interruption is what it does. So what you're going to do is you're going to just drop a little, I don't know, flag in the code. It's called a breakpoint. Whenever the code hits a breakpoint, it stops. So you can use this to flag parts of the code that you want to inspect very carefully. You can drop a breakpoint in front of a function or inside a function, and whenever the code gets there, it'll stop. And you can say, okay, now I'm going to start poking around. I'm going to start printing stuff. I'm going to look at the values of variables, see where the problem is. where things are. There are many commands associated with breakpoints. We're not going to go over all of them. There's a list of them right here. We're just going to use this first one, which is break. You can specify a file name. You can specify the line number that you want to put the breakpoint at, or you can just specify the function, which is what we're going to do here. We're going to put a breakpoint in front of read integer args right here, right before we enter it, so that we can go into this function and start poking around in there and see if we can figure out where things went wrong. Okay. Let's see here. All right, so automatic interruption continued. So I already listed, I'm going to list again 7 through 15. Those are my line numbers. So I want to put a breakpoint here. I want to put a breakpoint right at read integer arguments. When I do that, I'm going to start the code over again from scratch. And as soon as I hit that breakpoint, the code is going to stop. And then I can start marching into the code again before it crashes. Now, you see? So, excuse me. So I'm going to use the command break, read integer arguments. Okay, that's the name of the function right here. Okay, enter. And now it's going to tell you, okay, breakpoint at breakpoint number 1 has been added in file int_list_tools.c line 8. And that is right at read integer arguments, just inside that function. So you drop into the function, then you're going to stop right there. Perfect. Excellent. Now I can push forward. So now I'm going to use that command that I mentioned previously. I'm going to use run. Now, what does run do? If you don't remember, run is going to start the code all over again from scratch. So this allows me to start over now that I have an idea of what might be going wrong or where I want to poke around. I'm going to start over, but I do need to give it some command line arguments. Run. So I give it, in this case, 2, 3, 4, 1, 3, 5 in the slides, whatever. Okay, hit enter. And then it's going to say, I'm starting the code. Here's the code I'm starting. This is bug example, as we know. Here are the arguments that I'm using. Great. March, march, march along. Now, when you use run, you're going to run until either you crash again, which can happen, of course, or you hit your breakpoint. Now, in this case, we hit the breakpoint before we ran into the segmentation fault. That makes sense. Hopefully, it makes sense to you anyway, because we put it before some integers was called. Remember, this is the function here where the actual segmentation fault occurred. All right, so now we are sitting at int list tools line 8, which is the very beginning of read integers. Okay, great. So run Okay, now this is where one of the most powerful things that I find when I'm using a debugger. Not only is printing stuff powerful and adding breakpoints so I can start the code and stop in specific spots, and I can print out the values of variables. I can poke around all over the place inside the code with all the variables left intact. All the relationships between the functions are there. I can also march through the code very, very slowly. I can take it one line of code at a time. I can step, print out some variables, step again, print out some variables, step, 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 very slowly, so I can watch the code fail, or I can watch the variable take on that bad value. I can do it really, really slowly. We got a question. Is the breakpoint written into the code? No, it is not written into the code. It's just part of GDB. When you leave GDB, when you're done with GDB, your code is exactly the way it was when you started. You have not touched the code. That's the beauty of this. You're going to find your bugs, but you're not going to actually touch the code. To be completely honest, when I'm debugging a code, I'll usually have GDB open, but I'll also have my text editor open beside it. and I'll be looking at the code in the text editor. I'm not touching it, but I just use it to have a different sort of perspective on the code, right? I'll have several functions or maybe multiple files open so I can look at them. I can see the path of the code in my head. And then GDB has its own little printout of what's going on as well. But no, the code itself is never modified. That's one of the powerful aspects of all this. You can find the errors, and then you can fix them once, and that's it. You're done. No dinking around with breaking your code. Okay, so I want to step through my code now. I've hit my breakpoint. I've stopped. And now I want to start marching through my code slowly. Now, there are a number of ways you can do this. I usually do line by line. But sometimes you don't want to do that. Sometimes that can get a little bit tedious, especially if you've got code that you know works, right? So you can step into a function. If you bump into a function, you can go into it, or you can step right over it. You can say, I know this code works. I know this function is fine. I'm going to step over it. And that's also you can show the surrounding lines using TUI. We're not going to do that today, but I usually use next, which just continues, goes one line at a time. Stepping into the function is a useful one. Finish is also a useful command. If I've marched far enough through the code in this particular function and I know that I don't need to see any more of this function, I've seen what I need to see, I can type finish and it will just go to the end of the function, return, and then stop. And then you can carry on from there. You can also use the until function. This is also a powerful one, the last one here. And that means keep running until this line, so that I don't have to go through all 10,000 steps of that loop, right? If I've got some loop in my code that goes a long, long time, I can just march right past it. GDB, yes, thank you, Bruno. GDB-TUI can show the source code as you go through. That's true. That's probably the correct way to look at your code, is to use the TUI command. I like to have my text editor open, but either way will work. Either way will work. Where am I? Okay, so let's go here. All right, so now we're at the beginning, so let's do list again. So we are in this function. Here's our read integer arguments again. And here's the code that we want. I'm going to do a little more. I'm going to do a list 6 through 14. I want to see a little bit more of the code. So there's our function. We're going to march through here. Okay, and now I'm going to use the display function. We talked about this before. So remember the difference between print and display. Print will just print out the value of a variable once, that one time that you ask for it. Display is going to keep printing that value of the variable after each command that you type in. So I've got this variable called result. That looks promising in terms of probably what I'm after from this function. I'm going to say display result. Okay, so it immediately says, okay, here's the current value of the result variable. It's nothing. And that makes sense because we're currently at line, what line are we at? Frame. We're currently at line 8. Okay, the beginning of line 8. Result hasn't even been allocated yet, right? So result has no value, but that's okay. We're going to march through the code now and watch what happens to the result as we go. So I'm going to use next. Okay, remember what next does. Next is going to march one line of code at a time. Okay, boom. So I hit next. Now I've moved to line 12. I'm going to list again. I'm at line 12. Also notice that result got printed again, and result now actually has a value, right? We've got a proper memory address for the result variable. Great. Okay, so we came down. This is the beginning of the function. We got result got allocated. Great. We passed over int. I has been initialized but has no value. And now we're down at line 12, the beginning of this loop. You can see it right here, right? For I is 1, I less than n, I plus plus. If I do next again, it will get to the next value. Okay, great. Now I'm on line 13. If I type next again, I'm back at line 12, right? This is a for loop. So it's going to go down and up and down and up and down and up because it's a for loop, right? It's looping. That's what it does. Great. Excellent. Okay, now, so we can see that the value of result is getting printed each time. Excellent. We see that result's been initialized. Now, I don't want to go through all the iterations of this loop, though I don't think n is very large. Yeah, n's not that large, but nonetheless, I don't want to be here all day. We've got better things to do than watch the debugger print out the same result for result. So I'm going to use the until command. I'm going to say, okay, where am I? I want to come down to line 14, the end of this loop, after the loop is done. So I'm going to do until 14. So it will run through the loop for me and it'll stop. And then, of course, once again, the value of result has been printed out. You'll notice it hasn't changed, right? It's still 602010. Okay, great. All right, now, okay, so I'm happy I've gotten through the loop. Now I'm going to type finish because I'm done with this function. It seems like everything's okay. Finish. Okay, great. So it says it's going to run until it exits that function. That's what's happening here. Okay, and now we've popped back out at line 9 in process.c. The value returned is 0x4 as opposed to 0x60, what was it? 602010. Something went wrong there. Wait, hold on a minute. What's going on here? Clearly something's gone wrong because the return value is not the value of the result. Something's not right here. Okay, what's going on? Let's look at it one more time. List, read, integer arguments. So you can not only list where you are, but you can also list functions. I'm going to do +7 because that will give me 7 extra lines. Read integer arguments. Here's the read integer arguments function. We were just here a second ago, right? And you can see right away, oh, yeah. I forgot my return statement. Look at me, I'm an idiot. Yay. I said that a lot as a grad student. This is the normal side effect. Okay, so this example has demonstrated much of the functionality of GDB, right? We entered into a function, the code, we looked at the stack trace, we printed out some values of variables, we popped out of the function, we added a breakpoint, we reran the code until we hit the breakpoint, we poked around some more, we entered a function, we printed out values until we found the cause of the problem. The cause of the problem was lack of return statement. The reason why the pointer, which was returned by the function, did not have an allocated value or a value allocated to it is because we didn't return it. Oops. Okay, great. So here's a review of many of the functions that are available. This is by no means complete. You'll notice a couple of the functions, the commands that are part of GDB that we actually used are not on here. Frame, for example, is not on this list. This is just a reference point for you, so you have something to get started with when you go down this road. Of course, Google's your friend as well. There are tons and tons and tons of tutorials out there on how to use GDB. But hopefully what we've seen here so far is a good introduction. Okay, questions so far? That sort of ends our GDB portion of the class. We've got a couple more slides. We're going to look at Valgrind. But before we do that, let's just get any questions if there are any. Okay, excellent. Now, sometimes you suspect or you know that your code has issues with memory, especially when you've got a code that has a lot of arrays or it could be an MPI code where you've got lots of pieces of arrays that are moving around and you've got lots of bookkeeping going on, and it's hard to keep track of all your indices and making sure everything's lining up really well. It can sometimes be really hard to keep track of where things are going wrong. You don't always get a segmentation fault when you have a memory problem, right? Sometimes things just work and you get the wrong answer and you don't know why. There's a bug in there somewhere, but it's not causing the code to crash. That's the worst part about it, is that it's not crashing. If it crashed, you'd be a lot easier to track down where the bug is. If it doesn't crash, it can be challenging. And that's where Valgrind comes in. So Valgrind is a code, a debugging program, which intercepts every memory call and checks them to make sure they're correct. So all the reading memory calls, all the writing memory calls, all of these calls are checked by Valgrind. It's a free open source code. Every time I see the name, I want to say Valgrind because that's what it looks like to me. It looks like that to everybody, Valgrind. Apparently not. If you go to the author's website, it's supposed to be Valgrind. So that's what I'm going to try to remember to call it. It's really, really good for illegal memory access, uninitialized values, memory leaks of every kind, all kinds of memory use problems. However, the biggest downside of using Valgrind is that it's really verbose. That means it barfs out a huge pile of text onto your screen every time you use it. That's just the nature of the animal. It's just really, really verbose. Especially with external libraries, this point here. External libraries, you can sometimes get a lot of false positives. So you have to be careful. Try to focus on your own code when you're using Valgrind and not to worry about external libraries. Okay, so I'm going to run Valgrind on this code. I'm going to exit GDB, quit. Yes, thank you. Okay. And I'm going to run Valgrind here. Valgrind, bug example. Give it some arguments. Okay, so now you can see there's a lot of text here. It goes on and on and on. Here's the call way up here. And here's the report. Now, here's the first thing you want to notice about Valgrind that distinguishes it from GDB. And that is that GDB allows you to, as I said before, sort of live inside the code. You can dive in, be present, poke around, march through, inspect live as the code is executed by the computer. Valgrind is different. Valgrind is strictly a reporting utility, right? You run it on the code, it's going to do a report on your code. It's not going to let you go in and poke around with the memory, at least not with memcheck, which is what we're using here. Rather, it's going to give you a report, and that's what you see here. So let's just go through this here. So by default, it uses a function or a package called memcheck, which is a memory error detector. Just slide this over a little bit so it's a little easier to read for you. Forgive me for making my slides really tiny. So, okay, here's the command. So you can see immediately it's detected an invalid write in this function. Down here, it's going to see there's an invalid read in this function on this line. Process terminated with a segmentation fault. No surprise there. We knew that because we haven't fixed the code. Access not within the mapped region at this address. Yeah, well, there's no surprise there. We saw that in this function. Very good. Okay, and then it gives you some other information here. Okay, as I said, very verbose. There's lots of information in there, but also very powerful. Very powerful. It takes a little while sometimes to grind through all of this text, but there are a lot of clues in there that will help you understand where the code's going wrong and what types of errors are being performed. Okay. Valgrind gives you a report on the code rather than letting you actively explore it. Using Valgrind on mature codes often shows a lot of errors. This may or may not be an issue. Valgrind has a habit of generating false positives. so you have to be careful about that. Generally speaking, when I'm using it, I only focus on my own code. If something else is giving an error message from some library that everybody uses, I try not to worry about it. Best to use it early in the process of developing your code, right? You've got your functions, you're writing modular code, you've got your test routines, you can run Valgrind on the individual testing routines and make sure everything is behaving properly. Apart from the basic usage, there are other tools available with Valgrind to deal with many other aspects of memory management and memory access, cache performance, memory leak information, race conditions, all kinds of goodies are in there. So if you go down this road, I highly recommend you get used to Valgrind and its reporting abilities. They're pretty powerful and very, very useful. Questions? So we got some references here. That's all I had for today. Other than presenting the assignment, if there are no questions, we'll do that quickly and we'll call it a day. Is the assignment only the code? Whoa. 1 through 5. Okay, hold on. Let's go. Let me get to the assignment here. How do I pop out of this thing? There we go. Okay, excuse me. Okay, so assignment. Here we go. Okay. Now, right, we were discussing this before, my colleagues and I. We're not totally sure about this. We've set the due date for 12:30 just before class starts on Thursday. If you guys are having problems with the assignment and think that you need some help, or maybe we need to push that due date a little bit, let us know and we can talk about it. I think it's a pretty straightforward assignment, but that's easy for me to say, right? Elena's asked what about where the code is that we will use for the assignment. Just bug example is the answer to your question there, Melina. Just the bug example code. So here's what I want you to do. You're going to download the code. This link here just points to the file on the front page, the tarball. So that tarball contains all the code that we use for this class, which contains all of the DDT and MPI codes and CUDA codes and other codes that we may play with and may debug either Wednesday or Thursday. We're not going to use those for the assignment. I only want you to look at the bug example code for the assignment. The code that we played with today as our example, that's the code that I want you to consider for the assignment. Okay, so using GDB and Valgrind, debug the code. So we found one bug, fantastic, that's great. There are more in there. There are several, and Valgrind hinted at it, right? It hinted at a few different bugs that are floating around in there that we didn't talk about. You may have seen them as I went through the code. Maybe you didn't. That's fine. So all your assignment is to debug this code. Okay. For each bug you encounter, I want you to print out the values of the relevant variables. I want you to give me the stack trace. I want you to copy and paste that output into a text file. Maybe put some comments in saying what you see and what your approach is going to be to solve the problem, how you're diagnosing it, what the problem is. I want you to fix the code. Okay. When you're done, there should be no errors reported by Valgrind. There are many reported right now. When you're done, it should be clean. Should be no errors reported. You should get a very short report out of Valgrind, which essentially says, ding, it's squeaky clean. Put your text file and your cleaned up and improved code, upload it to the assignment Dropbox, and that's all we're asking from you. Questions? Are there any options? Oh, this is a good question. I've been meaning to get to this, but since DBS is brought up, are there any options for Python? The answer is yes. DDT can do Python. There's also PDB, which is the Python debugger. Again, we're not going to be covering these in this class, but they're out there. PDB in particular is built similar to, not built, but feels similar to GDB in a lot of ways. So that is an option for debugging Python code. Other questions? No? Okay, well, in that case, thanks, guys. And of course, if you have any questions, shoot us an email, or there's always the class forum we'll be monitoring as well if you have questions. And if not, we'll call it a day. Thanks, guys. Oh, here another question. Can I comment on IDE debuggers like Eclipse? My comments on Eclipse are not for public consumption. We don't like Eclipse. I actually don't know. I have very, very little experience with it. Does anyone from the team have much experience with Eclipse? It's been a long time since I touched it. No? Yeah, I don't have anything to say. DDT or total view? Sorry, I don't understand the question, Melina. What are you trying to ask? We'll be using DDT. We'll do DDT tomorrow. But as has been pointed out, you do have to pay for it. It's worth paying for. But fortunately, we've already paid for it for you, so you're good to go. All right, cool. Thanks, guys. Have a good day. I'll see you tomorrow.